So in chapter 11, we're going to talk about linear equations. And a lot of these ideas are things that you're familiar with in algebra, but we're going to extend it out to hypothesis testing. So in 11.1, let's talk about the linear equations here. And notice that here the equation is given in the form of y is equal to a plus bx. In a traditional algebra class, you might have remembered as mx plus b, where we had the m was your slope, and then the b was part of your y-intercept there. So we're changing these a little bit here. In this case, our b is going to end up being our slope. And then our y-intercept is going to actually be the point 0a, and that'll be our y-intercept. So just a bit of notation change there, but again, they're just variables, but just to be clear on that. And then if we recall about slopes and how these linear equations look, you could be kind of increasing, going upwards. You could be kind of just flat horizontal with a slope of 0, or then going downwards where you had a negative slope. So just some characteristics of that. And so let's start off with a problem here. So example 11.3. So Aaron's word processing services does word processing. The rate for service is $32 an hour plus a $31.50 one-time charge. The total cost of a customer depends on the number of hours it takes to complete the job. Find the equation that expresses the total cost in terms of the number of hours required to complete the job. So this is pretty typical. You might take something in to get serviced or looked at, and there's a flat rate of what they charge just to kind of look at your stuff, and then they'll have, an hourly rate on top of that. So let's let X be the number of hours to get a job done here. Let me actually put that number of hours to get a job done. And we typically refer to this as the independent variable or the explanatory variable. And let's let y be the total cost to the customer here. And that's sometimes referred to as the dependent variable, response variable, even a predicted variable, we'll start seeing in this chapter. And so we're going to start off with the equation y equals a plus bx, where our y-intercept, again, is a 0. And actually, I have that swapped around. It should actually be 0a. There we go. And a is our initial value. So a is 31.50. So, it's a one-time fixed cost just for Aaron taking kind of the job, right? So just for kind of looking at it. So that's going to be our y-intercept there. So that's the interpretation of it. The initial value that we have. And our slope here is a rate of change. And so you might recall from algebra, y2 minus y1 over x2 minus x1. I like to refer to it as the change in y over the change in x. So it's a ratio of those two. And so in this case, our b is $32 per 1 hour. And so that's technically a unit rate. So if we wanted to interpret this verbally, we say for every hour on the job, the cost will increase by $32. And so our equation here is going to be y is equal to 31.50 plus 32x. And so if we were to plot this here, so on our x-axis, we're going to have hours here. And then we're going to have total cost, because that's the way it wanted us. It's at a total cost to number of hours here. And so right here is going to be our y-intercept, right? That's where our initial value is, and that's where we hit that y-axis. And if we apply the slope to this, what it's saying is for every hour increase, we're going to go up about $32. And we could do this several times if we need to, right? Every time you go over an hour, it's going to go up another $32 or so. So a rough sketch of our graph would look something like this, increasing. And again, you have an arrow off to the right because it could take, who knows how many hours this task could actually take. And typically in a lot of real-world applications, many times we're really only going to deal with the first quadrant. So because the lowest cost you could have is $0. So it really doesn't make sense to have a negative x in this case. Although there are times when you could have negative values, but typically for money or time, things like that, we won't have that. So notice we're starting at the 3150 here, and there's no arrow going pointing towards downwards. Okay. So let's look at some scatter plots here. And we're going to go ahead and use the same example here. So here's our equation of 3150 plus 32x. And we're going to just create some values. Many times it's kind of done backwards where you have a table of values and then you kind of get a scatter plot for that and try to get an equation. But let's go ahead and do a little chart here. So similar to what we would have done in an algebra class. And let's just pick some common values here. So maybe one common value here would be, let's say, 0 hours. So maybe Aaron has a lot of people who come look at, take something to get looked at, and then they probably don't proceed with it or so. So he charges just that initial fee of $31.50. So let's plug in 0 into our equation, and then we would get $31.50 there. So maybe some other common tasks, or maybe an hour or so. So let's try x is equal to 1. And I'm just making up these x values. I'm just plugging in. But again, they could probably be some common, rates that from the past that are pretty typical. So jobs taking an hour. And I'm going to plug that in to our equation, and we get 63.50. And let's do a few more here. So for x is 3, our y will give us 127.50. For x is 5, our y will be 191.50. And then for x is 8, it's going to be 287.50. So maybe these are just some common hours that he has. He probably never works over a full day's work of 8 hours there. And these are going to be enough for us to just go ahead and do a rough scatter plot here. So x-axis is going to be hours, and then on our y-axis, we're going to have money here. And so on the y-axis, again, a lot of times the point of a graph is to make something that's nice and clean. So I don't have to actually label exactly 3150 or 6350 or 191.50. I'm going to just pick some values that are nice and clean for us, and then we'll kind of just fill these in where they fall at. So that first point, 3150 is going to be somewhere around there on that y-axis for x is 0 here. And then we could do another one. So at x is 1, this is roughly about 63.50 there. I think we're just doing a rough sketch here. And we're going to want to do this for all of them. So at 3, we're going to have roughly about 127.50 there. At 5, we'll have 191.50, so slightly below 200 there. And then also for 8, we'll be a little below 300 there at 287.50. And notice here we are not going to connect the dots here. We're just making a scatter plot, so not graphing the linear regression. And when we talk about scatter plots, we like to see if they have kind of a positive kind of relationship or a negative relationship. And you could think of this as kind of the slope. If it's increasing, going upwards, we say that that's positive. So overall trend here is increasing for these top two graphs here. So we say that that is going to be a positive linear there. Okay. The second one is also positive, but there is one kind of straggler here that kind of deviates a little bit. But apart from that one, the majority ends up being fairly linear there. And you could also have a trend that's decreasing. And so these guys are going to be kind of negative. And we also want to talk about the strength of it. So since this is kind of closer to a straight line here, we see that that's stronger as opposed to the second one. If I were to try to connect kind of a line that fits through most of these points here, it's not going to be that close to the majority of the points, so there's going to be kind of some discrepancy, right, between the line and the actual point. So it's further away from all of them. So even though it's negative, we would call that it's a bit more weak. And there are other types of trends beside linear. You could have non-linear, so this is kind of an exponential curve here. And then you could have something that's just scattered all around. So we would say that this one down here has really no pattern. It's just kind of completely scattered, so no trend there. We're going to focus on linear regressions here, but just be aware there are other types of regressions that could fit other models.